is Neha Rajput, and welcome to my talk. Power electronics is a ubiquitous technology found in many day to day applications. In any power converter, passive components are one of the bottlenecks, and magnetics typically occupy 40 to 50% of the converter's weight and volume. To develop power efficient and power dense magnetics for the next generation power electronic converters, one needs to select the most suitable magnetic material from the many available options. For this selection, accurate core loss models are essential. However, modeling core loss in magnetic components is quite challenging. First, due to the nonlinear characteristics and saturation behavior of the materials, and second, because magnetics are subjected to non-sinusoidal excitations under varying operating conditions of frequency, plug density, temperature, and more. In the literature, various empirical models such as classical Steinmetz equation and invariants have been developed to predict core losses for different excitations. However, these models have limited validity across frequency and plug density ranges, offer low prediction accuracy, and are typically applicable only to specific waveform types. In recent years, machine learning has shown great promise across many fields of engineering, including power electronics, owing to its ability to model complex nonlinear relationships. Such models, however, require large-scale core loss databases for training and testing purposes. These datasets can be generated using specialized testers capable of producing different waveform shapes under a wide range of operating conditions. In this work, we utilize the core loss database provided by Princeton University to train and test our proposed model. The proposed approach combines the advantages of machine learning and empirical modeling. A feed-forward neural network is employed due to its simplicity and ability to handle scalar inputs. In the pre-processing state, scalar parameters are extracted and fed into the network. In this study, we selected the classical Steinmetz equation and improved Steinmetz equations, as these models also operate on scalar inputs rather than time series data. Based on the conditions defined by the duty ratio, the appropriate empirical model is chosen. The Steinmetz parameters from this empirical model serve as learnable parameters within the neural network. The network then learns the complex relationships between the scalar inputs and the power loss through these embedded empirical models, creating a reciprocal knowledge transfer between the two approaches. This hybrid model, therefore, is called the empirical model informed neural network, or in short, MPIN. The first version of MPIN was submitted to 2023 Magnet Challenge, where it was tested across 5 different grades of ferrite materials. This version received an honorable mention in the competition. In the newer version, several techniques were implemented to enhance the model accuracy and reduce model size. For instance, data binning was used to make the Steinmetz parameters adapting over smaller frequency ranges. These improvements led to better accuracy, smaller model size, and increased generalization capability across all prime materials. In summary, a simple feed-forward neural network combined with empirical models for different excitations, augmented with techniques such as data binning and oversampling, resulted in a highly accurate and generalizable MPIN model for core loss prediction.